Who said it?
Cool. I think we're good to start then. Today we're very happy to have Arthur visiting us and telling us about some higher axions in particular.
Thank you for the introduction, Amin. I just want to start off this talk by saying that Seth Corn and I went to a Chinese restaurant a couple of days ago, and the fortune cookie revealed this wisdom to me. So keep this in mind while I sort of get on with my talk. So I'm Arthur Platschorre. I'm a endowment fellow at Cornell University. And the research that I've been interested in so far is taking aspects from the more sort of formal side of particle physics, such as, for instance, these generalized symmetries, and I'm trying to apply them to more cosmological side of physics, such as, for instance, the nature of masses of new particle candidates. Today I'll be presenting some research of mine with Mario Rieck and Vajra Lolat that is very much in line with that sort of ethos, which will be about axions which have two key properties. And the first one is that they have an exponentially high quality. And the second is that they have a very predictive cosmological scenario. Okay, and I'll spend the next 5 minutes sort of trying to define what I mean with all these different things, but also to motivate why you would be interested in axions of this nature. Okay, well, as you're well aware, there's a sort of ever-growing experimental program dedicated to finding the axion, finding QCD axions, given how compelling they are as solutions to several standard model or cosmological puzzles, such as the nature of dark matter or the Frank speed problem. For the QCD axion in particular, what a large fraction of these sort of experimental searches do is they are smaller scale resonant searches that try to resonantly enhance the axion signal right around the axion's mass. And what that means is that by design, these experiments can only scan a very small part of axion parameter space at any given time. And sort of scanning even sort of the QCD axial mass parameter space, it becomes now something on the order of decades. Okay, so the holy grail of axion physics is to provide an estimate for the mass of the axion, or at least sort of benchmark window that you can then pass on to experimentalist friends. Common observable that has been, this is amazing, this blackboard is so wide. A common observable that has been used to sort of estimate the mass of the axion is through its sort of cosmological influence.
You can put a vertical line and divide the blackboard in several sections.
Don't listen to him.
You know, you find it too wide.
No, I like that it's too wide, but I've only crossed the line once and actually crossed the boundary.
Very good, very good. No, I thought that you were complaining.
It has to be a sort of boundary in my story, and then I cross the boundary line.
And that doesn't look vertical at all to me.
So one observable that's sort of commonly used to estimate the mass of the axion is the axion's local energy density in the universe. So rho of A, the axion's energy density, I'm going to lift this ever so slightly, is 0.4 gigaelectronvolt per centimeter cubed times 5.8 microelectronvolts for the mass of the axion to the power of 6 times some initial angle. And then what you can do is you can just equate the amount of axions energy density that you expect to the amount of dark matter energy density that we have observed, and you get an estimate for the mass of the axion. Okay? There are multiple caveats with that statement I just made, and two of those are going to dominate the discussion for today. So the first caveat is that if you want to have a QCD axion, then you want your axion to satisfy an additional property, and that's that you want to have it be of very high quality. And what I mean by that is that the dominant contribution to this axion's potential comes from QCD effects, and any other effect is extremely suppressed. Okay. There's a second caveat with the statement I just made, which is that I haven't explained part of the formula to you. Okay, so this part, A initial, is called the initial misalignment angle of the axion. And what it measures is how much is the axion angle of at the start of its evolution from the minimum that will eventually be generated by QCD effect. Okay, and having a very good prediction for that initial angle is what I call, well, what I will refer to as very predictive cosmological scenario. So I wouldn't be here today if there isn't an issue. So the issue is that in sort of conventional axion models, there's usually a tension between either obtaining a very high quality and obtaining a very predictive cosmology. So to sort of illustrate that, for complex scalar axions, sort of the most conventional axion model, what you'll find is that in the best case scenario, you'll have a very good prediction for your cosmological scenario, but these have notoriously a very poor quality. On the other, let's say, end of the spectrum, you have these extra-dimensional axions. And with extra-dimensional axions, you often get a very high quality, but we'll see during the talk that you get a very poor prediction for this initial angle. Okay, so there's this sort of tension in axion model building. And to me, this presents a very nice, and there's a third caveat. Okay. And the third caveat is that this formula doesn't actually capture all of this sort of axion energy density that you can get in the universe. Sometimes during the axion's cosmological evolution, topological objects involving the axion can appear, such as, for instance, axion strings, axion domain walls. And these can actually also contribute to the energy density of the axion. And numerical simulations actually find that these can dominate the energy density of the axion. So with ordinary sort of dark matter predictions, you would predict some mass of the axion, which is in this sort of few micro electron volt range. Whereas if you have additional contributions, then the mass of the axion can be much larger to equate the same dark matter distribution, which means that numerical simulations find that the mass of the axion, once you start including these strings, can be pushed up to something like 50 micro electron volts. Okay, but to me, that is a sort of more numerical aspect of this issue. And I'll focus on trying to resolve these more theoretical caveats. Okay, but nonetheless, I think it provides a very nice place where sort of theory, numerics, experiment all come together to sort of drive the future of this aspect of particle physics. Okay, so the sort of resolution of this tension that we want to work towards is going to be that we're going to take these sort of conventional axion models, these complex scalar axions and the extra-dimensional axions, and we're going to try to mix them to sort of get a model out that has the best of both worlds. The model that does that I'll present today involves one other non-trivial ingredient, which is the Green-Schwarz mechanism, or a sort of analog or generalization of the Green-Schwarz mechanism. Now I should be careful, but nowadays the sort of ungauged version of the Green-Schwarz mechanism is known by the sort of the umbrella it falls under as higher groups in this sort of generalized symmetry language, and that's why we've dubbed these axions higher axions. Okay. What we'll find is that the ingredients I sort of introduced today will also all be present in string theory. So if time permits, then what I want to do is I want to do a sketch of sort of the string theory scenarios that we had in mind to create these axions. But I also want to show you some additional complications that you run into in string theory model building that have to do with supersymmetry. Okay, so the outline of the talk is just, I'll first go over these conventional axion models, so these complex scalar axions. I'll run through both the quality and the cosmology. I'll do the same thing for these extra-dimensional axions to contrast it to the first sort of case. And then we'll go to these higher axions, introduce the sort of minimal ingredients one needs, and then I hope to be able to sketch what happens in the string theory scenario. Has that raised any questions?
What makes truth higher?
I think it's sort of the other way around. I think that the truth lies in the higher sort of version of the axioms.
Okay.
So now I've crossed Carlos's boundary, and we'll go over into sort of this first scenario, which are these complex scalar axions. So with complex scalar axions, what you have in mind is that there's some complex scalar which has a U1 symmetry, and that U1 symmetry at some point during the cosmological evolution is spontaneously broken, and the axion emerges as the Gaussian boson of that symmetry. So you have some complex scalar phi that at some point in the universe reduces to a VF times e to the I the axion. Okay. For today, what we'll always keep in mind is that the symmetry is only broken after inflation. And the reason is that it will give you the best sort of predictive cosmological scenario for these complex scalar axion models. Okay. To sort of see that, let's trace through the cosmological evolution. So at temperatures which are larger than sort of the spontaneous breaking scale of the symmetry, what happens is that, well, what happens during the universe is not that interesting for us right now. But what happens right as the temperature drops below the spontaneous breaking scale of the symmetry is interesting. And what happens is that the axion suddenly emerges as a degree of freedom. Okay, which means that at this time, there are loads of causally disconnected Hubble patches. I'm going to draw 5 because of the Olympics. And in each causally disconnected Hubble patch, the axion takes a different value. Let's say A is 0, A is pi, etc. Now, the universe cools further and further, and at some point QCD effects turn on, and the axion in each of these patches starts running down towards its minimum. Now, what's going to help us in this case is that our current Hubble patch makes up a very, very large number of these Hubble patches at this initial time. Okay. So the axion value we see is a very, very large statistical inference over sort of all these initial axion values. Now we know that the U1 symmetry at this time was not explicitly broken by QCD effects yet. So what that means is that the initial distribution of these axions will be roughly uniform. And if you're doing a statistical inference for sort of the axion value you see in your Hubble patch from a uniform distribution, that will just be A squared initial is pi squared over 3. Okay, just from plugging in the uniform distribution. Okay, so that is why in these sort of post-inflationary axion scenarios, which is scenarios where the symmetry is only broken after inflation, you get a very good prediction for this sort of cosmological initial angle that the axion has. Okay. Now, that is one aspect. The other aspect is this quality of these sort of complex scalar axions. And in order to see that the quality is quite poor, what you want to do is you want to sort of remember your EFT rules that you learned, which is that you should write down a Lagrange for these axions, which is compatible with all the different symmetries in your model. Okay. Now, unfortunately, we know that the U1 symmetry of this axion will already be broken by QCD effects. Okay. So we can't use the U1 symmetry in order to suppress the U1 symmetry is not part of sort of these EFT rules for which operators you will be able to write down. So for instance, your Lagrange will involve a term which is something like phi to the n over whatever effective cutoff of your theory to the power n minus 4. Okay. This breaks this U1 symmetry of the complex scalar. Now, for the QCD axion, it turns out that even if you take the cutoff of your theory to be m Planck, so you expect the U1 symmetry to only also be broken by gravitational effects, for instance, then these operators need to be suppressed to a very, very high order in order to still have the QCD axion solve the SOM-CP problem. Okay. So for sort of generic ranges of this decay constant of the axion F, what you need is that these operators are suppressed from anywhere between order 8 to order 12. Okay, so that's the first order at which these operators can appear. So that sort of extreme sensitivity of complex scalar axions to these sort of UV effects has in the literature been dubbed the axion quality problem. That is all I have to say for complex scalars, apart from the fact that an incredible amount of work has gone into trying to resolve the quality problem of these four-dimensional axions. Mostly what they focus on is trying to assign additional gauge charges or symmetries into your theory in order to suppress these operators up to a certain order. Okay, so these are these Zn axion models, or you can have composite axion models. And what happens is that you sort of polynomially increase your quality of your axion, but you start introducing additional effects into your cosmology, such for instance relic densities or domain wall problems that sort of model up this cosmological predictivity. Okay, that is the sort of let's say state of the art of these complex scalar axions. Now I'm gonna.
Yeah. Raise that and lower that. Yeah.
This is not the right one.
That is the right one.
No,
Raise that.
yeah, I understand, but now you can't see.
Lower, no, lower the other one. Lower the first one. Lower that one. Now you have continuity, you see? There you go.
You're a genius.
My mother tells me that.
So I want to contrast this scenario with these sort of extra-dimensional axion scenarios, which have gained a lot of traction in sort of extra-dimensional model building, but also, for instance, the string theory literature. The example I just want to run down is somehow sort of the simplest thing you can think of, which is one extra dimension, which is sort of compact. Okay, so you have four-dimensional Minkowski space and one additional circle. And on that circle, we'll have some coordinate that measures the angle. Let's call it phi. And what I'll do is I'll identify phi with minus phi, which means that on the circle, you're identifying sort of all of these points. And instead, the extra-dimensional circle becomes an interval, which has two endpoints, 0 and pi, which are invariant on the identification. At some point, we'll start putting matter fields at these endpoints. But for now, I'm just going to introduce what the axion is. So in order to get an axion out of this extra-dimensional model building, you have to put something in the extra dimension. And for a one-dimensional higher extra-dimensional model building, what you do is you put in a gauge field. So we put in some bulk gauge field, A, where A is some gauge transformation. A equals to A equals D of lambda. Okay. Now, as a sort of low-energy observer, the only thing you'll see is the average over the extra-dimensional circle, which means that the only thing you'll see from this gauge field is exactly the average, the angle bone phase of that gauge field around the extra dimension, which gives you one axion. These axions, just like the complex scale axions, have a shift symmetry, a U1 shift symmetry, which shifts the axion by a constant. Constant, I mean, zero. Okay. And I want to convince you now that these sort of, this U1 symmetry is very different from the complex scalar's U1 symmetry. Mm-hmm. And the reason is that I'm telling you about the UV realization of the symmetry. So in the IR, we observe the symmetry as that of an axion. In the UV, the same symmetry is that of the gauge field. Okay. So the gauge field has a symmetry. You can't write these transformations as a gauge transformation, so it's a genuine symmetry of the gauge field. And I want to first sort of appreciate what the charge operators are under the symmetry, so we can understand what the symmetry is. Okay. So the only gauge invariant operators that you have in a gauge theory are Wilson lines. And these Wilson lines are just some integrals of e to the IA around any sort of closed cycle. Under this shift symmetry, what happens is that these Wilson lines shift by a phase. Okay. So this is a U1 symmetry. Now, this U1 symmetry doesn't act on sort of, in this case, on lower dimensional operators, such as, for instance, fields, but it's acting on line operators, so one-dimensional operators. So in the literature, these things have now fallen on the what are called not zero-form symmetries, which are these symmetries that act on fields, but one-form symmetries, which are symmetries that act on lines. And you can generalize this as you wish. And this symmetry is a U1 one-form symmetry, which is quite a mouthful, so it's usually written as U1 to the 1. Okay. And the axion, this shift symmetry of the axion that you eventually get in the IR is a zero-form symmetry. It acts on the axion, but it has come down from one of these one-form symmetries. And that's why we'll keep writing these symmetries like this to keep track of this sort of UV realization of the symmetry. Now, what I want to convince you is that these symmetries, enjoy a much better protection than these sort of complex scalar U1 symmetries. And in order to show you that, I just want to envision somehow some effect that, for instance, breaks the shift symmetry of this axion. Okay. Now, this axion is an Arnold bone phase around the extra dimension. So the only thing that can break its shift symmetry is some effect that is sensitive to the entire extra dimension. Okay. What that means is that any effect contributing to the potential of this axion yep, that's the right sign, will be suppressed by the action of that effect. Okay. That effect has to go around the entire extra dimension. So if it's, for instance, created by a particle of mass m, then we know that let me just write it like this. E to the minus the action of that particle will at least be smaller than e to the minus mass of that particle times the radius of the extra dimension. Okay. So that is why these sort of UV realizations, or these U1 symmetries that come from sort of extra dimensional model building, enjoy a better, in this case, exponential protection than these sort of complex scalars. That's why I like to keep track of these symmetries. Now, where you gain some, you lose some. And what you lose is this sort of cosmological predictivity. So imagine heating up the universe well beyond sort of the inverse size of this extra dimension. Okay. What's going to happen now is that I don't not only care about the average of this gauge field, but I will start caring about all the KK modes of this gauge field, all the higher KK modes. Now, even in that scenario, the axion is still a well-defined degree of freedom. It's the average of the gauge field around the extra dimension. So this is very different from the complex scalar scenario, where if I reheat above the sort of spontaneous symmetry breaking scale of the scalar, I no longer have an axion. Okay. So what that means is that these kinds of axions are also around during inflation, unless you prevent it with some additional model building, which means that during inflation, this axion will also take some values into each sort of causally disconnected Hubble patch. But now the exact opposite is going to happen that happened for our complex scalar scenario, because our Hubble patch is actually a very, very small Hubble patch in one of these Hubble patches during inflation. Okay. So what that means is that the initial axion value we see in these scenarios is completely random. Okay. So generically, unless you do some additional model building, these extra dimensional axions are of a pre-inflationary nature. Good. If there are no questions?
So I guess in the previous case, if you just actually extrapolate all the way back to inflation,
Yes.
then don't you get a similar story too? Because somehow everything emerges from one patch.
No, because at some point the complex scalar will go through zero.
Oh, I see. And then
Like you
axion
can't talk about the axiom before the.
I see.
Okay, so now let's move this one up. So this is sort of the tension that we're sort of faced with right now. And we want to sort of resolve this in a way that we get the best of both of these axion, complex scale axions and these extra dimensional axions. Okay. So this is what we got in my paper, higher axions. Although there are other extra dimensional model building scenarios that you could have in mind in order to resolve this issue. So in order to appreciate what sort of you want to do is let's just start with having both these axions present, the complex scalar axion and one of these extra dimensional axions. And I'll denote them by their symmetries. So I have one U1 0 of the complex scalar axion, and I have one U1 0, which has come down from 1. Okay. And I want to get one axion at the end of the day. So what I'm going to do is I'm going to introduce one more gauge field into the problem, which gauges some diagonal combination between these two symmetries. Okay. So that's some U1 gauge. So in symmetry space, that's a U1, that's a U1, and I've gauged some diagonal combination. What that means is that I'm left with one of the U1s which can form my axion. Okay. And I claim that in the IR, this is the way to get these nice axions out. And the way that, so we can run over the same things as before. So why does this axiom have a nice quality? Suppose you have any effect that sort of breaks the shift symmetry of this axiom. You can never break the gauge direction by definition. And what that means is that you always have to break exactly the orthogonal direction. The symmetry space. Okay. Which means that you always have to go through both symmetries. So you'll always be protected by the exponential protection of one of these by the exponential protection of the extra dimensional symmetry. Okay. So you still inherit this nice quality. Now, to see that you still get this very predictive cosmology, imagine again leading above the spontaneous breaking scale of the complex scalar. Then what you have is you have a massive gauge field and a complex scalar that is charged under that gauge field. Okay. So during inflation, there was never a sense in which you could talk about the axion. But as temperatures dropped, and now all of a sudden the complex scalar symmetry is spontaneously broken, you'll now get a gauge invariant direction that is the axion, which is sort of the difference between the two phases if you've gauged them both with charge 1.
Can you say what is the 5D action that realizes that gauge quotient?
I will, yeah, so this is the IR story, so I'll now go to the UV story. So I'm gonna have to introduce green spots if I do that. So unless there's a nuance that someone thinks I missed, I will now go over.
Can you say again why you can't just linearly redefine your fields to make it look like a standard U1 and some trivially gauged one?
Why you can't make it look
You're
like?
gauging the diagonal U1
Yeah, that's right.
in this case, and your axion is the difference.
Yes. So you can do that redefinition. The point is that you want to preserve that one of the symmetries is exponentially good.
Yeah.
And that you're sort of showing in this direction. You can do the same thing as you're saying, but you're now sort of justifying that scalar that you will get out, which gets restored above the phase, will have an exponentially good symmetry because of its sort of extra dimensional realization. So that is why I'm keeping track of this symmetry. But you're right that you could redefine it in that sense. Okay, so in the UV, we once again have this Oberfold scenario in mind where we have an interval with two endpoints. And I'll put both the complex scalar and this gauge field, which I'll call C, which has nothing to do with the gauge field A, at one of the endpoints of this interval. C has some gauge symmetry. C goes to C plus d of lambda C. Okay. And now in the IR, we had that this extra dimensional axion was charged under the gauge symmetry, which means that somehow in the UV, we have to charge a gauge field, in this case, this gauge field A, under the gauge symmetries of C. Okay. Now C lives at the endpoint of the interval, which means that the only thing we can do is A transforms on the gauge transformation of C by a delta function times lambda C. Okay. And that might look a bit weird because we don't often consider sort of localizing gauge transformations. But it turns out that these things are well known in sort of the analogous scenario which occurs in string theory. So to do that, I'll just introduce all the analogous elements in sort of the string theory scenario, which goes by the name of the Green-Schwarz mechanism. So in string theory, you have a field B mu, which is sort of the analog of our gauge field A. There will also be a gauge field C that B mu transforms by. And there will be yet an additional gauge field, fourth gauge field, a third gauge field, which has some field strength F. Okay, so F is the field strength of some additional gauge field in our string theory. Now, as solutions to the equations of motion as the vacuum manifold solution in string theory, what you can have is you can have these different fluxes. Okay, and these fluxes are sort of topological objects where this field strength F evaluates to a delta function. Okay. So the similar mechanism that we're going to need involves the exact same ingredients. So we have this gauge field A mu. So sorry, so this is the Green-Schwarz mechanism. And this led to a second superstring revolution, quite important in the sort of string theory area of things. The analogous thing we need is we have a gauge field A mu. A mu transforms by A mu plus lambda c. And instead of the field strength of something, we need something with one index lower. So we'll have it transformed by the d mu of some scalar alpha. Okay, where alpha is some 2 pi periodic scalar. And now what you need in your extra dimension is not just the ingredients, but you also need that the scalar d mu alpha is a domain wall. Because on the domain wall, what you get is that d mu of alpha is exactly a delta function. Okay. So the extra dimensional scenario I have in mind is not that of just an overfold, but on top of that overfold, you have a topological object, in this case, a domain wall.
Is there a version of this that could have worked if we had a circle and not an interval?
If you had a circle and you just had one, but you still put a field at a certain point at the interval on the circle?
No, I just meant is there could we have done a version of this where all the fields had some full 5-dimensional realization?
You mean put one of the you essentially want to ask whether you can put the complex scalar in the bulk?
Yeah.
Not that I'm aware of right now.
So it's important to have this like hybrid dimensional
Yes.
system.
Yes, because exactly of the sort of two different qualities that you eventually ask of the ax. So that's it for these sort of high axions. Now what I want to show you is that all these ingredients are sort of, I've talked about this a lot. All these sort of ingredients are sort of also present in string theory. Okay, in string theory, the analog of this is sort of this, and this will this occurs all over string theory, but the realization that we wrote down in the paper is in a sort of heterotic, where sort of this is indeed the sort of axions that you would be talking about. Let me also introduce you to one more model that does the same thing, which was not written down by us, but at the same time by Giovanni Villadoro and Rudin, which instead put two complex scalar fields at two different endpoints of the interval and have a gauge field that runs in between, such that in the IR, the only thing that you can write down as a gauge invariant combination is this. And the only thing that you have is one axion, and you will find that this axion has the exact same side properties. And this is a bit closer to what happens in, for instance, type 2B scenarios, where you have, for instance, branes that intersect at two different points. You can have scalars living at the two endpoints and gauge fields that go in between the two that live on the branes. Okay.
Can I ask a little bit about the higher dimensional solution to the quality problem that you're advocating for? So it still seems to me, maybe it's just a philosophical question, but it still seems to me like it's contingent on kind of an additional tuning step, which is the fact that the matter fields charged under the higher dimensional gauge field happen to be massive and happen to be quite massive in some units. If we had light fields, then we wouldn't have any suppression at all, and we would be in the same situation.
Well, light in the sense of masses, or light in the sense of so there's a slight so I would say that for massive fields, you have an exponential suppression, and that if you sort of count things by the normal counting, which is sort of we think of these parameters as sort of the orders that we work in, and not the exponent is the order that we work in, then I would say that provides you, if that is your philosophy, then this provides you with a solution. It is correct that if you have a massless field in the extra dimension, or something very close to massless, then that, of course, is not the action that you would be writing down for the extra dimensional contribution. Instead, what you would be writing down is just something like an instanton, like e to the minus 8 pi over g squared. But there would still be an action that you would write down. It's just not that. It's not that.
Well, it's just not exponentially suppressed in the mass, right?
No, there is an exponent.
Then it's a coupling question again, right? So, I mean, I guess what I'm trying to say is that there isn't a symmetry protecting the axion in either case. Whether you have massive, as soon as you have charged fields, the symmetry that you're talking about, that namely the one form shift symmetry, is explicitly broken. So you can be in a regime of parameter space where the quality problem is small, like you are right now, but you can also, it's a question of where you are in the parameter space. If you have massless fields, if you have order one couplings, then the quality problem would be quite severe again.
Correct. But my philosophy is that I want to be able to write down a model in the UV, where I know that generically it will flow to a model in the IR where the axion will be well protected. And it's not necessary that I protect it against. So I agree with you that if in the UV I introduce massless degrees of freedom, then that will not flow to an axion which has very good protection.
But how is it better than just being in the UV in a four-dimensional theory and explicitly not writing any other symmetry violating terms besides the instanton generated ones in QCD?
Because now you will still generate all these terms as you go down.
You'll generate them, but you'll generate them, won't you generate them through instanton effects in QCD because that's the leading violating?
Well, no. So that is what you're assuming. So you're saying that that would be the leading violating term?
Well, I'm saying I can assume that just like you can as my UV starting point, and just like you can assume in your UV starting point that that the effects are small through this mechanism. I'm trying to compare these. I'm trying to force you to defend why one is better than the other.
So the reason that I'm sort of more firmly defending the other is that we have a good UV realization of what these extra-dimensional axions would be like, which is string theory. And there I can explicitly show you these sort of what the correction would be. And so there, the trick is of course that I'm assuming with what particles are there in the UV.
Okay.
So string, yeah, so we're gonna do some string theory. Carlos, which one should I use?
I tend to, well, now there is no continuity. Yeah, the first one.
Middle front back, middle front back.
Sorry, yeah.
I think it's always. I think it's
middle.
always
No, you
middle
repeat
front
the
back,
cycle.
Middle front back, middle front back.
You repeat the cycle, but you didn't.
I've broken the epicycle and so.
Yeah, correct. So, but we have to go back to the first, right?
How about I write the conclusion on the first one? Is that, yeah.
This looks good. This looks good.
So in string theory, the ingredients of string theory, at least it's sort of low energy realization, is a NS1 at minimal sort of NS1 supergravity theory in 10 dimensions. Okay. What that means is that we'll at least have a gravitational field. It's super symmetric particles, which are beaming nu. And to complete the sort of supersymmetry, we need beaming nu and now, we don't live in 10 dimensions, we live in a 4-dimensional world. So if you want to maintain a certain amount of symmetry, you need to compactify string theory on a special kind of manifold. Okay. So the ones that are usually used are the ones that maintain the NS1 supersymmetry of the 4-dimensional theory. And the reason you do that is that you want to have a good handle on what your compactification results in. Okay. So otherwise your compactification can become sort of very unwieldy very quickly. These manifolds are called Calabi-Yau manifolds. And the Calabi-Yau manifolds have generically sort of internal cycles. They can in fact have quite a lot of internal cycles, 2-dimensional cycles, 4-dimensional cycles, etc. And on these 2-dimensional cycles, we can evaluate, for instance, the average of beaming nu. Okay. So for each of those 2-dimensional cycles, what you get is you get an axion. Okay, so this is one example. There are different ways to get axions out of string theory, but at least this has sort of led to this picture that you expect to get a lot of axions out of string theory, which is known as this sort of axiverse. Okay, the reason so that is important. The reason that I like axions from string theory is because they can give you a handle on the UV theory from sort of probing the IR dynamics. One way is the sort of very obvious thing, which is that the number of axions is somehow related, well, to the number of cycles that you get in the internal space. Another way is that one thing axions can probe is whether your UV theory is, for instance, a cut. Okay, so axions, or at least the QCD axion, is sensitive to both the coupling to photons and the coupling to gluons. But if you have a cut, then these two eventually in the UV are somehow related. Okay, and this can give you bounds on where the axion can lie in the axion parameter space. And various realizations of, for instance, string theory, at least string theory model building, have involved guts where, for instance, in heterotic, where you have an E8 cross E8 symmetry, you put all of the particles in one of the E8s. Okay, so here you have an axion on which you can have some bounds, given that your UV theory is a gut, for instance, and this allows you to probe at least sort of this part of string parameter space. So that's why I like axions. They are somehow low energy probes of UV theory aspects. These string theories will also sort of have all these other ingredients that we want. So for instance, we want to have complex scalars. These you can get from, for instance, having these fluxes that I introduced before, and zero modes of gauge fields around these fluxes can, for instance, form a complex scalar. And you will also have generically gauge groups, which can lead to sort of this additional gauge field C that you wanted. Okay, so far so good. Everything will run through in the same way as we did before. The issue in string theory is not the extra dimensions. The issue in string theory is trying to preserve the SUSY. Okay, so SUSY will generically relate different scales across your problem. And one way that shows up is sort of that all the different corrections to your vacuum energy, for instance, have to cancel. Okay, so one contribution that we'll get to the vacuum energy in these theories comes from the fact that all these particles are charged under the gauge field C. Okay, that leads in SUSY to a contribution to the vacuum energy, which is known as the D term. And based on the charges, you can write down sort of what the D term is, which in this case is Q times phi squared for complex scalars. For these fields, it will depend on the Kähler potential SUSY that you have. But I'll just write down the one that you, for instance, get in heterotic string theory, which is the charges of those axions times some number kappa I over kappa. I will not explain what these numbers are. Instead, what I will say is that they are related to the size of the inverse cycle, to the size of these sort of extra-dimensional cycles, okay? Which is clear from the fact that we also get phi, which is sort of related to the decay constant of these other axions. Okay, so just the decay constant of both axions enter in the D term. What that means is that now, sort of generically,
the first term is Qi phi I square also.
Yeah, if you have multiple scalars charged on the C, that's right. And the square of this will show up in the potential, and it has to be 0. Okay, so this has to be 0 in order to preserve this supersymmetry. Now, what this means is that if you want this to be 0, then what you expect is to have a scalar which has roughly the same sort of sizes as the cycles in the experiment. Yes, go ahead.
Are the KIs like charge fields?
So the KIs are functions of the. Sorry, the KIs are not fields. They are just functions of the sizes of the cycle. Just like here, you have a function which is setting the scale of which sort of the axions decay constant for complex scalar axions. Here you have a function which is related to the decay constant of these axions. I can write down the function.
The size of the cycle is dynamical, I think is what his question is.
I see. And these so right, okay, so this is charge under U1.
Under this C, yeah, that's what I just see. I can write down the formula for the for what is kappa usually, but don't think it will be very illuminating. But what this just means is that if you want this d term to be 0, then your complex scalar will roughly have a VEF that will be set by sort of the internal string scales. Okay. So in these models, what you sort of would get out is something like 10 to the 16, 10 to the 17 GeV as a VEF for your complex scalar axion. Which means that if you want these axions to show up in a post-inflationary scenario, you're really pushing the temperature at which you can still reheat the universe. Okay. So this we don't want. We want to avoid this to get an axion out which has slightly lower decay constant. Okay, something that is more in the sort of range that we like, which is like 10 to the 8, 10 to the 12 GeV. The way to do this is that in this internal space has a lot of different cycles, which means that you might end up in a nice point where sort of two contributions which are just as large cancel on this additional contribution from these internal cycles. Okay. So there are special points on this supersymmetric moduli space, which are called split loci, where essentially the term associated with all these internal cycles is very small. Okay. But all of these cycles are still large. Okay. And that is how you can get one of these sort of high axions out. Now that is a bit disappointing because I didn't tell you whether you live close or far away from these cycles. Okay. That is a question of moduli stabilization, and something that I'm now interested in with the people at Cornell, which have a very good program on trying to understand these axions out of string theory, is whether indeed after moduli stabilization you would find yourself close to one of these split loci, and in that case, do you get a post-inflationary axion out? On top of that, is that one post-inflationary axion you're getting out actually coupled to QCT? Okay. So I've introduced these sort of additional complications that you get in string theory. I sort of show you roughly what a solution would be, but it's still not clear that these axions you would actually get out of string theory, and that is sort of one of the things that I'm working on with these people. So I mean, like Liam McAllister's group and his very excellent students. I promised Carlos something.
Sorry, the compactification. You're talking about on a smooth Calabi-Yau, or do you need some kind of orbifold or something to generate? I asked you whether you could do a model in 5D without singularities, and you said you didn't know how.
Yes.
What's the manifestation of that statement here?
So the manifestation of this statement is that you're already localizing things by having fluxes in the extra dimension. So just like the domain wall, this string theory has, we'll now run over a specific example then.
Okay.
So the specific example I have in mind is in electronic string theory. And electronic string theory has these gauge fields, E8 plus E8.
I heard about it.
And what you can have is you can have fluxes in these gauge fields. Okay. So on these fluxes, what can happen is that you can localize one of these scalar fields. Okay, just as like we localized the scalar on the domain wall we had before. And that is sort of the models that I'm talking about right now.
What do you mean by saying the scalar is localized on the flux? What do you mean by that sentence?
So if you were to look at, for instance, there was actually a full batch of good chalk here, I mean. Was it? Yeah. If you look at, for instance, where these fields are coupled to the other fields in your theory, so roughly at sort of the wave function spread versus the wave function spread of the other parts of the theory, you'll find that you get a scalar which is very localized near that flux.
I see.
So I can refer to specific models where you can actually.
No, I understand what you mean.
Okay.
Yeah.
I'm still going to say the specific model. So if you look at papers of Lucas and Bookbinder and others, and Andre Constantine, you'll find that they've written down exactly a heterotic E8 cross E8 model where you would get one of these high axions out, although they haven't shown that you localize near the split. That is an assumption going into the paper.
And say again what the split loci was again?
Split loci is sort of where the contribution from all these extra dimensional axions to the D term vanishes, even though individually none of the terms are small. So in old schools, so study before this time, the assumption was always that this is 0, so you actually have to sit near the split loci, just because computation is easier. And now I'm saying that you want to sit slightly farther away from these split loci to get these nice accents out. So getting these exponentially good symmetries works for axions. You could have run this exact same program for instance, fermions. And for me, it's like a nice way to get lower dimensional particles to inherit the quality of higher dimensional symmetries. So
Conclusion. Not S.
sorry?
No, the section is usually called conclusions.
Maybe he only has one.
Maybe there's one conclusion.
I mean, I'm not calling it discussion, so that's why I'm sort of giving you my opinion and I will leave the room afterward. So the conclusion is that I sort of introduce you to sort of this tension in axion model building, which is getting an axiom which has two of these nice properties. Okay. We saw that the minimal ingredients to get one of these nice axioms out occurred when you started mixing these conventional axiom models, these complex scalar axions and these extra-dimensional axioms. Okay. The model I introduced right now needed some analog of the Green-Schwarz mechanism. A version of that falls under sort of what is now the higher group literature, and that's why these called the higher axions. Now, I also tried to sketch that in string theory, you might be able to end up with these axioms, but there are still additional hurdles you would need to overcome. Okay, but what this does for you, if you do so, is that you get a post-inflationary axion out of string theory. Okay, and that might be your best hope of nailing down the mass of that axion if it's a QCD axion. Okay, and that's sort of what I aimed on. Thank you.
Questions for ethics?
So I'm wondering, but there is no low energy property that I can identify.
Good.
Because, yes.
So there's one additional field that kept hanging around, but I never sort of talked about, which is that you also get a massive gauge field. Now, the mass of that gauge field is related to the size of the extra dimension, which means that as I start doing away with the mass, if I want that gauge field to go away, I will want to push up its mass. But what ends up happening is that I pull down these contributions to the axion's potential. Okay, so here's the game you're playing. Let's say you know what contributions you would get to the axion's potential, and that would give you an upper bound on the mass of that gauge field, which is sort of there to protect the axion. Okay? So here's sort of what would be one of these measurable consequences of at least these sort of high axion models. Okay. Is that satisfying? Okay.
Okay, so is it correct to say that like as I lower the mass of the gauge field, the axion becomes higher quality? Or is it?
Yes. But at some point you also start seeing the gauge field. So like
if you want it to be, I mean, if you want to solve the quality problem well enough that like, we would have already seen non-zero data,
yeah, that's well.
how light does it have to be?
Depends on what order. So you can write down ordering operators and assume that you're just spoken by gravitational effect.
Yeah.
And then you can make an estimate for the mass of the gauge field. I've not done the back of the envelope. Someone could check that one.
I'm curious, can you say a little more about how you stabilize the moduli? You mentioned, so you said you do it with gauge fields. What kind of potential do you get generic? So like a specific case that you're studying, or is it like a generic thing that you can stabilize moduli?
So in this extra-dimensional model building, I didn't mention these moduli at all, and that's because sort of stabilizing the radion can be a tough thing to do, and that is why I'm not necessarily claiming. So I'll go string to you in just a second. Why sort of these models are not complete in the sense that the thing that's protecting you is the size of the extra dimension, and you've not stabilized that size in any way. You've just imposed the size upon it. In string theory, what you get is that you'll get a superpotential which is proportional to e to the minus these moduli. Okay, and that will so there's that contribution to the moduli which you'll get. Now you're still in a supersymmetric theory. So if you now also want to go to the standard model, you also have to introduce supersymmetry breaking into your theory, which can further sort of complicate the potential you would get for these moduli. So Lee, McAllister, etc. are now sort of at least estimating the size of all these different contributions to this moduli potential. So all these different e to the minus moduli plus e to the minus moduli. But a full sort of calculation that I can give you for these high axions I wouldn't have yet. Okay, because you would also have to introduce the supersymmetry breaking on top, which you can, which they claim to now be able to do. But there will be exactly these contributions that we saw to the axion potential, this extra-dimensional case, but then also because of supersymmetry involving the modulus of that axion, so the size of the extra-dimensional cycle. That is basically what they look for. Yes.
I have more psychological questions. So then, would you say that this quality problem is severe enough to, in general, pay more attention to other solutions of the strong CP problem, like the spontaneous parity or CP violation?
In just the standard model, or if you have some extension of the standard model? Because that will...
It's always an extension, I believe that.
So
because you need to put it in some context. Yeah.
So in a sort of extension of the standard model, I'm also... if you give me the UV is just a standard model, I would not be too, which you can't, but if you, let's say,
in general, I put something else.
Okay, then I would be worried about the strong CP problem. But if you just tell me that it's just a standard model, then the sort of contribution that you would get from, for instance, weak sect CP effects is very, very small, much smaller than the sort of current bound that we have on theta.
No, I mean, the strong CP problem is, as we know, serious.
Yeah.
We believe, probably it's irrelevant, but we believe that it's very serious, and the axion looks like the most natural realization, but has all these problems associated with it, right? And then that we have to deal with, that we ignore usually.
Sorry, I thought you said you solve the problems.
Yeah, you emphasize the problem. So the question is, and now it looks to me some sort of miraculous realization of this to be the QCD axion, right?
Things are not miraculous because what I've done is I've told you what the UV realization of the theory is, and in that I've sort of resolved.
But you didn't. I didn't hear the word QCD anywhere here. So you have to make the...
Yeah, making this couple to non-abelian gauge fields does not seem trivial.
Well, the non-abelian gauge field has to live in the extra dimension, then it's fine.
Okay.
What is non-trivial is how anomaly cancellation works in these theories, because you have a delta function localized gauge field. And that turns out to be very close to what happens in M theory, anomaly cancellation, where sort of... Well, okay, that's fine. Yeah, yeah. Okay, I'll keep it at that. Hangame, you also had a question?
I would gonna like ask later, but just like sort of coming back to Clay's question on like having massless like modes like kind of ruining the quality, because I thought even if you have like these massless modes in you still get the suppression exponential for the potential of your axion in the 4D just coming from the volume of your extra dimension. So it's always like the volume that's kind of like protecting you. So I was a little confused by like how like the mass was playing into it.
So what happens in the massless is that it's not a volume protect. Well, you can think about it in different ways. So let's say you have an axion and you have extra dimensional QCD. Then we know that the contribution to the potential of that axion is going to be e to the minus 8 pi over g squared. So you'll still get an exponential protection, and that charge will be set by sort of the extra dimension, in the sense that like you would evaluate it at the size of the extra dimension, but it's not. I'm not claim. No, I would never claim that sort of the charge is proportional to the size of the. Well, you can write it. Okay, I guess you can write it in a way where you can write this as the 5D g squared
Yeah.
And then there has to be an R either at the top or bottom for dimensional analysis. I forgot which one. Probably this one.
Are you talking about the effects coming from non-abelian gauge fields?
Yeah, if
Yeah,
you
but
would have,
there will also be direct effects coming from the light charge scalar,
yes.
right? That would not be suppressed by that.
Let's see. So for a light charge scalar,
The direct comparison, the direct comparison to your e to the minus mr is not to compare to the non-abelian gauge field potential, but to the effect of the massless charged scalar field.
correct. The thing that you get in that case is so if you have a massless scalar, then what you get is a potential which will be of the form 1 over the size of the extra dimension, so polynomial extra dimension, which I think was what we were saying, times cosine of the
Exactly. Yeah.
So it is true that this sort of exponential suppression makes the implicit assumption that I know what is happening in my okay, and that is where you get the good quality from. Okay, but here is a UV theory, so let's try to figure out whether you get these nice axions out of it.
If there are no more questions, let's thank Arthur again.
How'd it go?
I think it was last part. I got the last part. I think the instruction was not weird.